Let's suppose that we have a rigid body way out in outer space. No forces are acting on it. In particular, there are no gravitational forces acting on this body. Now, there's a smooth axle that the body is free to rotate about. So, this smooth axle we can imagine is fixed. It could be fixed to a spaceship. Okay. Now, the axle is perfectly smooth, so the body can rotate about the axle with no resistance to its rotation. So suppose that a force is applied to the body at this position here. Well, we know from Newton's second law that if a force is applied to a particle, then the particle will accelerate. Now, as long as the force is acting, this particle wants to accelerate in the direction of the resultant force, of course. But it can't do that because the entire body is constrained by this axle. So what will happen, of course, is that the body will rotate in this direction, clockwise, about the axle. Now, what's going to happen when the force vanishes? Okay, so you can imagine that the force acts for a very brief amount of time, then no forces act. Well, we can imagine that the body will keep on rotating forever about this smooth axle, because the axle applies no resistance force to the body. Okay, so the body is turning in this direction. If there was friction here, if the axle wasn't perfectly smooth, then the axle would exert a force on the body in this direction. Say, at this point here where the axle is in contact with the body, we would have a force that's resisting the motion, and the body would come to a stop eventually. So, this is analogous to Newton 1. This is shorthand for Newton's first law. If we have a particle that's moving with a certain velocity, v, well, if no forces act on this particle, if the resultant force on this particle is 0, then the particle will move with velocity v forever. Now, you might say that there is a force on this body, and indeed there is actually, because the body is in contact with this axle. Okay, I'll just remove this force here because there's no resistance force. So what is the force on the body due to the axle? Well, we will show in a later video that that force is on a line that's joining the center of gravity of the body. Well, there's no gravitational force acting here, so we can call this the center of mass. Okay, we'll discuss more about that later. So there is a force on the body, but that force, as you can see, acts in a direction that's perpendicular to the direction of motion of the rotating body. Okay, because if we imagine the axle is in contact with the body at this point here, well, this point in the body is moving in this direction, perpendicular to the force on the body. Okay, so this is the force on the body. It's not necessarily the same as this force here, of course, so I should probably not call it F. I call it a different name, or maybe I won't call it anything. Okay, so this is the force on the body, where the body is in contact with the smooth axle. Okay, if there was a resistance force, then the axle would exert a force in this direction on the body, tangential to the axle, but this force doesn't exist. So anyway, this force here is perpendicular to the part of the body that's in contact with the axle, so it has no component. If it has no component, it does not change the speed of this part of the body. So the speed of this part of the body that's in contact with the axle is constant. As a matter of fact, the speed of all points in the body will be constant. But the velocities are constantly changing. So this is the interesting thing. So this is how it differs from Newton's first law. In Newton's first law, we're dealing with just a particle. The velocity is always constant. If the velocity is constant, the speed is constant. So if the velocity is v, the speed is v, without the arrow. Okay. So The speeds of all these points are constant, but they all have different speeds. You know, this point out here has greater speed than this point here. Okay, so here we apply circular motion. So the speed of the body depends on how far away it is from the center of rotation. Now I should say that the quantity that's constant is the angular speed omega. So again, in Newton's first law, we're dealing with the resultant force F on the particle. The resultant force F is 0, so the particle moves at constant velocity v. So the speed v of the particle is constant. Here it's omega that's constant. The speed v of a particle depends on the distance r of it to the center of rotation, to the axle. We saw in the section on circular motion that if that distance is r, then v is omega times r. Okay, so that's for this particular particle here. But if we take this particle over here, we can see that this particle is further away from the axle than this one is, so we expect the velocity to be greater. Okay, so this is a greater r, we could call it capital R. So this capital V, if you like, is omega times capital R. But omega is the same for all the particles. Okay, the angle swept out by either this line or this line in unit time is the same. Okay, the angle swept out is omega radians per second. Now, what about the kinetic energy of this point here? Well, this point is part of the body, of course. Its mass is delta mi. So it's a very small particle that makes up the body, but it's not an infinitesimally small particle. Okay, delta means it's very small but not infinitesimally small. So to get the kinetic energy of any body, we have to multiply half its mass times its speed squared. So let the speed of this body here be v sub I. So this is the ith particle in the body. Okay. Now, the reason I say approximately is because delta mi is not a particle. Okay, it's so, you know, this part of it has lower speed than this part out here. Okay, if it's a point particle, then we can say that the kinetic energy is exactly a half times the mass times vi squared. So, you know, when we use calculus language, we would let delta mi approach 0, and we would replace delta mi with dmi. Use the differential d in calculus. So this would be the exact kinetic energy of a point particle of mass dmi. Okay, but we will just stick with the delta mi for now. Now let's consider the kinetic energy of the entire body. So we define that to be the sum of the kinetic energies of all the particles that make up the body. Okay, so delta mi is of course just one of the particles. So we've got to imagine summing all those particles. The particles will have different speeds vi depending on how far away they are from the axle. You can see that vi is proportional to ri. You know, if we double the radius, the distance of the particle to the axle, we double the speed. Okay, you can see that from the formula. vi is just a constant omega times ri. So vi varies. The further the particle is from the axle, the greater its speed, vi. So we write sum over I. So I ranges from 1 up to whatever number of particles make up the body. You know, we could have a million particles here, 10 to the power of 6. This is only an approximate kinetic energy. Of course, in reality, well, for calculus purposes, we would let delta mi approach 0, and then our kinetic energy formula would become exact. So the approximately equals would become an equality. Okay, we'd replace the sigma with an integral sign, the delta mi with dmi, and we'd have vi. Well, we'd have some formula for v. But anyway, we won't be worrying about calculating this thing. We'll just work with the sigma notation. But in general, of course, this sigma here becomes an integral as delta mi approaches 0. Okay, so we'll just leave that out for now. We'll see more about that in later videos. So we're summing from I equals 1 up to some extremely large number, okay, depending how small our particle is. The smaller we make it, of course, the more terms we have to sum. Now, this half is just a constant that can be taken outside the sigma. What about Vi? Well, we can use the fact that Vi is omega times Ri. So Vi squared is omega squared times Ri squared. Now, omega squared is a constant. It's the same for all the particles. So this constant factor can be taken outside the summation. Okay, so it's Ri that varies. Okay, depending on how far the particle is from the axle, but omega is constant for all particles. Now, notice this quantity here. This quantity is very important. This is the sum of the products of the masses of each particle times the square of their distance from the axle. Okay, this quantity is called the moment of inertia of the body, and we will be calculating this quantity for various regular objects later on, like disks and rods. The capital I is used to denote the moment of inertia. So this is the formula for the kinetic energy of the body. Now really it's just an approximation because we haven't used calculus. We haven't let this quantity go to 0, but you know, if we do it more rigorously, we will get this formula here, half omega squared I for the kinetic energy of the body. Now, notice how this compares with the formula for the kinetic energy of a particle. So here we have a particle with velocity v. Okay, so no forces act on it, so I'm assuming that the resultant force on it is 0, so we know that it moves with constant speed v in a straight line. So if its velocity is v with the arrow, its speed is just v without the arrow. So its kinetic energy is half mv squared. So notice what's constant here in this formula. What's constant usually is the mass. The mass doesn't change, of course. It's just the mass of the particle. What's constant over here is omega, the angular speed of the rigid body. Okay, so the body's out in outer space. It's rotating about this axle. There is actually a force on the body due to the axle, but as I've explained before, that force is perpendicular to the part of the body that the axle is in contact with. Okay, so it doesn't slow down the rotating body. The axle is perfectly smooth, so the body rotates forever with constant angular speed omega, unless some force acts on the body, of course, to either increase its rate of rotation or decrease its rate of rotation. Right, so we're just comparing these formulas. So a particle with 0 resultant force on it, or a rigid body that's rotating around a smooth axle, so no tangential resistance forces acting, so it'll rotate forever with constant speed, angular speed omega. Well, I said that m and omega are constant, but what I really need to compare here are not m and omega, but v squared and omega squared. It's true, of course, that both m and omega squared are constant, but that's not what's important here. Okay, what's important is v squared and omega squared. They play analogous roles in the definition of kinetic energy for a particle with 0 resultant force acting on it, or rotating rigid body. It's rotating around a perfectly smooth axle with no forces acting on the body other than the axle. Right, so the other term is the moment of inertia. Now that plays the role of mass in this kinetic energy formula. So I'll highlight that. Okay, so these two play analogous roles. We know that the inertia of a particle is its resistance to changes in its velocity. That is, resistance to changes to acceleration. So the inertia of this particle is its resistance to acceleration. And the inertia is proportional to the mass. It's proportional to m. So as m goes up, the inertia goes up. Okay, the more massive a particle is, the more resistant it is to being accelerated. What about this quantity, moment of inertia? Well, this depends not only on the mass composition of the rigid body, but also on the position Ri of each of those particles that make it up from the axle. Consider these two bodies here. Both of these rigid bodies have exactly the same mass, capital M. But you can see in this mass, though, in this rigid body, the mass is meant to be evenly distributed throughout it. Okay, whereas with this mass, with this body here, the same mass M is all out in, say, the rim of this wheel. Okay, we have some spokes attached, but we can assume that the spokes are quite light. So here are the axles for both bodies, but both bodies have the same mass. Now, suppose we want to calculate the moment of inertia I for both of these bodies. Well, we'd have to take each particle that makes it up, get its mass delta mi, multiply by its distance Ri squared, to the axle. We'd have to do that for all particles that make up this body. And we get some number. We get some number I that we can call I. Suppose we do the same here. But notice here that we have the same mass, but it's further away from the axle, so the distance is greater for all of them. So the moment of inertia of this body here is greater than the moment of inertia for this body. So that means it's actually more difficult to turn this body. Okay, so that means that if we apply a force to the body here, the body will rotate about this axle. But if we apply the same force to this body here, okay, well, this body will also rotate about the axle, but this force has the same magnitude as this force here. And suppose that this force acts at roughly the same distance from the axle as this one here. Okay, they're meant to be the same distance. Let's just see that maybe a bit more accurately. So F would be more like here, I suppose. This body won't turn as easily, okay, because the mass is further away from the axle. Just like in the case of a particle, the greater this mass is, the more difficult it is to get it to move. Okay, so it's the same idea here. So that's why the word inertia is used. But in this case we're talking about rotational inertia. How resistant a body is to rotational motion. Whereas over here we're dealing with the inertia of a particle. How resistant the particle is to straight line motion. Because we're not dealing with rotation here, because this is a particle. It's got no dimension essentially. So we can forget about its rotational motion. It's a point particle. So to sum up, in the case of a particle, its mass m is a measure of its resistance to acceleration. We know that the greater the mass a particle has, for a given force, the smaller the acceleration. The greater the mass, as m goes up, the acceleration goes down, because F, the resultant force, is the mass of the particle times the acceleration. It's Newton's second law. Okay. In the case of a rotating body, I is resistance to rotational acceleration. So again, the body is rotating around a perfectly smooth axle way out in outer space, and its angular speed omega is constant. The greater I is, as I goes up, what happens is that the rotational acceleration will go down. Okay, and what is rotational acceleration? It's how quickly omega changes. So we use the letter A for the acceleration of a particle, but for rotational acceleration we could use omega dot, which is omega dot is just the rate of change of omega with respect to time. Okay, the change in angular speed divided by the time taken, dt. Okay, we can use that. What's often used is the letter alpha. Okay, so when I goes up, alpha goes down. So how do we make I go up? Well, we just spread out this mass, make it further away, make it, the particles that make it up a greater distance from the axle. We can keep the mass the same, the mass is m, but we can just change the configuration, so that we can increase or decrease the moment of inertia, because the moment of inertia depends on Ri squared, the distance of each particle to the axle squared. If we increase Ri, then we increase the moment of inertia. I goes up. Ri goes up, then I goes up. We don't have to change the total mass, so all the particles have the same mass. We could just imagine positioning them, giving them in a different position. Okay, so we can imagine different rigid bodies with exactly the same mass, but the ones that have particles that are far away from the axle have greater moment of inertia.